Yep, it looks good.
All right. All right.
Oh.
We rolling?
We are rolling,
All
everyone. We
right.
we got the technical
Sorry.
difficulties fixed here, and I'll leave it to you, Curtis.
All
Go
right.
ahead.
Okay. So of course, first things first, a cluster rocket is a rocket in which end motors fire simultaneously and can go from 2 to a maximum of, so far the record is 299 by Bruce Lee, and he did this with something called a flash pan, which is an advanced technique. My bio, did rockets as a kid, got involved in clustering, and the CMAS Club has two masters of clustering, Jim Fliss, who uh, encouraged cluster rockets, and Boris Gatan, who's the master of clustering as well, and took clustering to a new level. And of course, for those of you who know me, I'm just going to kind of breeze through these first couple slides again. I'm a fanatic about the upscale Deuces Wild, a canted cluster rocket, and deuce means two, so drag race. And I can certainly do this whole presentation about the deuces wild, but this is more general talk about clustering. So we're going to talk about the reasons why we can cluster, for things that can go wrong and how to mitigate, different rocket geometries. And we really like in a cluster, we really like to get all our motors to light. And then very briefly, some advanced topics. So why cluster? So in the early 80s, uh, we only had black powder motors. There's an inherent size limitation to the size of a black powder motor that you could build. So if you wanted a larger motor, you were forced for more thrust, you were forced to cluster and black powder. So, and then with ammonium perchlorate motors, of course, this issue went away because there's effectively no upper bound on the size of ammonium perchlorate motors. All right. What are some other reasons why people might cluster? Well, there's technical challenges of more complex construction, more complex motor mounts, getting things to align properly, and there's also the challenge of getting all the motors to light. And the technical mastery of the issues in clustering are also related to staging and air start. Now, another reason people clustering is that it just looks cool. So you can see on the left a tractor rocket with three clustered motors, which flies in a helix pattern. And on the right, you see three motors in a linear pattern with all the same thrust. Now, if you imagine just looking at the rocket on the right, if say the right motor doesn't go off, you have a thrust asymmetry about the center line, and that's going to give you a thrust imbalance. So that leads us into what can go wrong and how to mitigate. So what can go wrong? Well, the main thing that can go wrong in clustering is that not all your motors can light, and this can lead to thrust imbalances or not enough thrust to reach aerodynamic flight. And additionally, motors can come up the thrust at different time. Like you see these pictures on the right. This is a Deuces Wild, and it's one motor lit before the other one, and it's clearly off the end of the pad uh, before the second motor lit. You clearly want to be able to design your clusters so that a motor, so that your rocket can have a 5-to-1 thrust ratio on a single motor. So of course, with thrust asymmetries, you can have unstable or erratic flight, possibly unsafe conditions, or the rocket can even break apart from excessive forces. All right, so let's look into misaligned thrust a little bit deeper. So a a rotational force is known as a torque, consists of two components, a force and an action arm. Now that rotational force is going to get bigger if the force gets larger or if the action arm gets larger. And this is going to act to rotate the rocket. So in terms of clustering, the larger the thrust we have, the larger the potential is for rotational forces. In additional, because of geometries, we obviously can't have multiple motors on top of each other, so we have to space them out. And so the greater distance the motors are from the center, that's the greater potential for rotational force. So the mitigations, of course, are to keep the motors as symmetric as possible and keep the motors in a tight cluster to the center line. And additionally, you can increase the number of motors, say, as opposed to having two large motors, you could have six small ones. And if one of the small ones didn't go off, that would be have less impact than if one of the two motors didn't go off in the 2 meter scenario. Now, these are all thrust related mitigations. So the fins actually supply a restoring force, and you can make the fins larger to give a better, stronger restoring force. And the Fliskits Deuces Wild is an example of this. It has kind of massive fins, and that's going to help supply a restoring force. All right. So why even consider safety at all? So the NAR found in 2005, they did a study of the root causes of different accidents, and they found that overall the hobby is very safe. But one of the findings of that is that the complex multimotor rockets are twice as likely to fail as simple rockets. Now, what can we do about that? So I'm going to present this systematic risk management approach, which consists of 3 steps. So we're going to decompose a complex event into a sequence of smaller steps, and then we're going to identify the faults for each steps, and then we're going to apply mitigations. And our basic fault is not all motors firing, and the hazard that can result of this is either a thrust imbalance or insufficient thrust. And the goal by addressing all the mitigations for the smaller steps is that we're going to make the overall event less likely to happen. So, first step in this, we're going to risk analysis. We're going to decompose the events or the process into multiple steps. So if you imagine that you have a concept for a rocket in your head and eventually that rocket's going to lift off, what are the steps that have to happen in between that? Basically, for analysis, I'm going to divide it into 3 steps. So first of all, you need to design and build the rocket. And then after it's built, you need to stage it on the launch pad and set up the igniters. And then you need to launch and ignite that to lift it off. And these consist of smaller steps, which we're going to look at into more detail. So in terms of design and build, first of all, you're going to start out the smaller steps for this. You're going to start out with a design, a concept in your head, and maybe through analysis and open rocket analysis, you're going to come up with a design. Then you need to select the motors. You're going to build that rocket and select the starters. And in the setup phase, you're going to assemble your motors, insert the starters, wire the starters, and you also need to do lead management so that the the wires don't short. And of course, the wiring and the lead management get aggravated in clustering situations and more complex versus a single motor. And then in the launch phase, you're going to supply current, and that's going to heat up the starters, and the motors are going to come up to full thrust. So, and you can even decompose each of these steps into smaller steps, but we're going to stop at this level. So for liftoff to happen, basically all of these steps need to happen successfully, and they're basically some of these steps are more complex for clusters than for single motors. All right. So the next thing we're going to do in this analysis, we're going to put the different faults into a chart, or we're going to put these different steps into a chart, and we're going to identify all the faults that can go wrong. So, for example, in the design and build selection, you might select the motors improperly or have thrust in curve mismatches or not enough thrust. In setup motor assembly, you might assemble the motor improperly. In a lead management, you might have a broken connection or a short, and so on and so on. And I'm just giving you an example here. And you can also fill in the likelihood that these faults are going to happen on a qualitative scale of 1 to 5 and a severity from 1 to 5. And then the next step we're going to fill in for each of these faults, we're going to look at the ways that we can mitigate the risks. So what are the approaches that we have to lower or mitigate risks? So we're going to have 4 different approaches we can take. And the first one of those is by using independent redundant functions. And a good example of this is on a commercial airliner. So a commercial airliner has 2 motors, so engines. So you may not know it, but it can fly on a single engine from takeoff to cruise to landing. So that So the thrust function in an airliner is completely independent. So if one fails, you still have the other. Now, in terms of rocketry, and a good example of this is in dual deployment. So we often employ two altimeters for our charges so that both of those have to fail in order for the altimeter function to fail. Now, of course, this assumes that these functions are independent. So if, say, I have a battery, a single battery that supplies my two altimeters, um, and that battery fails, well, that's going to make both of my altimeters fail, and the altimeter function will not happen. So that turns this, so this common mode failure turns this AND gate into an OR gate, so that if the battery fails, both of those are going to fail. And in terms of clusters, um, basically the way to get kind of redundancy is again by taking two large motors or a few large motors and making it into equivalent number of more smaller motors. And another approach we have to risk mitigation is through careful design reviews. Um, and you can carefully make a design. You can, if you have questions about design, you can seek out a mentor, a more experienced rocketer, or put a post on TRF or the rocket or the NAR forum, and you want to test. And I can't emphasize the importance of testing. And another approach to mitigating risk is through practice and procedures. So if you have a set of steps and you practice it over and over again, you're less likely to make mistakes. If that if there's a lot of steps, you might want to create a checklist so you don't forget to do something. And practicing is also going to help you even identify all the steps that are involved. And it might help you might find, well, gee, I'm really not good at sticking the igniters in, so I need to practice that particular step even more. And then another way, well, you might just have to change and redesign things. Now, you can use these risk mitigation techniques to lower risk, but you can never ever totally eliminate risk. And you're going to have to ask yourself, is this residual risk something that I can accept? Now, you might just take a laissez faire approach and say, well, the NAR has liability insurance and that's going to cover me. But hypothetically, just think for a moment, what if there was you caused a very bad accident and there was a large liability payout? This could hypothetically raise the premiums for the NAR liability insurance, and that could hypothetically translate to larger dues. So the point here is that the actions of you as an individual could have much larger ramifications than you ever imagine, and could easily affect the entire hobby. So rather than make a mess and clean it up, let's prevent the mess from happening. So that's why we really need to develop a safety mindset to rocketry. Now, okay, back to our risk mitigation analysis. So we have these four risk reduction mitigation techniques. So then for each of these steps, you can apply these different techniques. For example, in improper motor assembly, you might practice this over and over again or have a checklist. Um, and for a vendor motor defect, you might just say, well, there's nothing I can do about that, but I'm just going to accept that risk. And for broken and poor connections, you might achieve that through practice and checklists. And if your battery not being powerful enough, you might mitigate that by testing. So the idea here is that by applying these mitigations, you want to kind of reduce this likelihood by 1 or 2 points, and that's going to make the overall process um, less less likely to have faults. And it's you're not going to learn this by me up here talking about it. So I'm leaving it to the reader to fill out the chart. And of course, you can divide up these processes and steps in ways that make sense to you. Is the way I'm doing it is certainly not the only way to do it. Okay, so in summary, risk analysis can reduce risks. This is I've introduced this one systematic process for risk analysis, and there's certainly others. And this analysis is not only applicable to clustering, but other aspects of rocketry, such as dual deployment. And our actions as individuals can potentially have ramifications for the entire hobby. So again, I can't emphasize it. Let's adopt a safety mindset to rocketry. Okay, So that's a lot of heavy material. So let's keep our eyes on the prize. We're trying to launch these um, exciting clusters. And on the left, you see a 3-engine linear geometry. And on the right, you see a canted 3 motors, a Fliskets Trez, and a canted design. So that's going to take us into cluster, motor, and rocket geometries. All right, and this pertains to this design and build phase. I'm going to try to have a slide or two on each of these different points. All right, so here we have different cluster, rocket, and motor geometries. And on the left panel, you see different and surround patterns. These are the default patterns that are available in OpenRocket. Another type of rocket geometry is canted motors, such as in the Fliskets Deuce or Trez. And another rocket geometry is having outboard motors. Now, with outboard motors, you have to be very, very careful because remember I talked about forces and action that rotational forces that get bigger as the motors get further from the center line. That's very much the case with outboards. Excuse me. So the best practice here is to, when you do outboards, is to have a motor in the center that's the most powerful, and the outboards should really just be kind of motors for show. Because if you don't do that and one of these outboard motors doesn't go off, that could create very, very big rotational forces. All right. And that takes us to, when you're considering different cluster geometries, you want to have thrust or your motors as symmetric as possible. And you want to have the same type of motors, at least in symmetric geometries. And if you have a central and motor with one in the center, you certainly want to put the higher in the center. And you also want to do analysis. If not all your motors go off, do I still have 5-to-1 thrust ratio with the remaining motors? All right. And clustering sort of amplifies build issues because small misalignments can lead to big rotational forces. And also with things like outboards, clustering the forces can be in different places than non-clustered motors. Oh, and a point I wanted to make out, we call clusters because we don't call the clusters multiple engine rockets. We call them clusters because, again, that emphasizes the idea that we want to keep the motors in a tight cluster around the center line. So in terms of the build issues, so maker technologies are your friend because with these techniques, you can design and 3D print or laser cut very precise geometries that'll give, especially in motor mounts, that'll give you really precise alignment. And you can create parts that fit together very well or even mate. And you can build alignment fixtures right in. So over here on the right, you see a Deuce's Wild motor mount, and there's a threaded rod here for alignment of the bulkheads. And the idea is that you take this out after you have built it, but you can actually 3D print a strut right in there and just leave it in the 3D printed part. So you can just build the fixtures right in the 3D printed parts. So again, so maker technologies are a means of helping you create more precise motor mounts and reduce that chance of thrust imbalances. So in your clusters, you need to calculate the net thrust. There's a handy dandy calculator online that you can use to sum up the thrust from different the motors that you select, and that can help you make sure that you have sufficient thrust. And of course, in OpenRocket or RockSim, there's a standard set of cluster geometries available. You can build other geometries and specify the tube as a motor mount. You want to set the motors to go off at the same time, and you want to have you can model canted motors, but you need to manually edit the ENG thrust curve file and with the cosine of the cant angle. And there's an Apogee newsletter that goes into detail about how to do that. And you can check your launch speed margins by selectively removing motors and making sure that you still have sufficient launch rail speed to have those aerodynamic forces take effect. All right. So in terms of composite motor selection, you want to pick propellants that light easily, such as Smoky Sams or Blue Thunders. CTI motors contain an internal pyrogen pellet, and Aerotech motors have a nice pyrogen pellet. And AP motors with smaller cores will light faster and have less variability in the time that they come up to thrust. So some composite motors that you want to avoid are motors with very short thrust, because if they go off at any time offset, that could give you very big forced imbalances. Also, with long burns, you need to be mindful in clusters that you'll still have a 5-to-1 ratio, and you want to avoid most green propellants. Also, older motors can oxidize, which can increase or cause them not to light or come up at different times. And color propellants, remember I showed you the picture back on the thrust imbalance slide of red propellants. They can come up to thrust at different rates, or they have more variability in coming up to thrust. And recommended low power motors are the D12, and for mid power, Aerotech F42 or G80s. And for high power, so I've had really, really good luck with Smoky Sams. They're really easy to light, and the sort of variance for them to come up to full thrust is in my anecdotal experience at least very, very small. So that's a good choice for high power clusters. And the dark matter is also, I like that a lot, and certainly I think my most favorite motor ever for clusters. And I'm not familiar with Loki motors, but I emailed Scott Cormier and he suggested the use of blue and white propellants. All right. So that's cluster motor and rocket geometries. So now let's get them all to light. All right. And this pertains to our fault analysis, these different steps of uh, starter insertion, starter wiring, and lead management, and actually the launch phases as well. So a black powder motor consists of some propellant and a nozzle. You insert a little SE's igniter, put the plug in, apply the current, and it lights very quickly. And composite motors get a little more interesting. Here's a cutaway of a composite. The parts are grains, and you can see here an igniter. With this blue part here is either a resistive chip or a little filament that has pyrogen on the end, and the pyrogen heats up and lights the motor. So uh, a composite motor, as you can see, there's actually a whole set of steps that have to successfully happen, and you can certainly extend the fault analysis, the risk analysis, to lighting up of a motor, because there's a lot of things that can go wrong. For example, your leads can short, your filament can break or get damaged. You can have too little pyrogen and it cannot heat up enough to light the motor, or you can have too much pyrogen and it can cause the motor to snuff out or even KO. And as I also, when this pyrogen goes off, it causes the end of the motor to burn, and that sends a pressure wave down the length of the motor, and that starts the edges of the propellant to burn, and then it comes up to pressure. So the point is that this takes a lot of time to happen, and there can be different variability in the time that it takes to happen. All right, so let's look at starters. So on the left, we have an Estes igniter. It has two open leads, a little pyrogen, a little filament with pyrogen on it, and open leads, which have a tendency to short very easily. And these igniters are very, very fragile too. Um, Also, in terms of the pyrogen material, there's at least kind of three generations of pyrogen. In the old days, there was a nice pyrogen that lit really well. More recently, there's a white cellulose pyrogen that it's terrible for clusters. They just do not relate reliably, and I would certainly recommend dipping those igniters, as I'll talk about later. More recently, they've changed the pyrogen again, and I don't have much experience with that. Uh, and over here on the right, you have a composite igniter, which I talked about in the previous slide. Okay, so for low power starters, SD starters, as I mentioned, are very fragile. So I really, really love these MJG BP starters, which are over on the right, because they have a nice little pyrogen tip on a resistive chip. They have nice long insulated leads, um, which are those are very, very good for clustering. So for SD's igniters, I'd certainly recommend dipping them, especially if you have ones with the cellulose. You can just hold it under hot water and wash the cellulose off, and you can use Quip Dip or there's a paper in the references sections. Somebody did a study on different kinds of dips and things, and they found out that just even nitrocellulose with a little bit of black powder gives a great igniter, SD's igniter dip for clustering. All right, for high power starters, certainly you want to start with the manufacturer's recommendations. MJG firewires are good, or Aerotech First Fires or Quick Burst. So I want to caution you about dipping. High power igniters can lead to overpressure and either cause a KATO or snuff the motor out. So I would for HP igniters, my advice is don't do it unless you have a reason to. B, you know what you're doing and have tested things, and C, you're willing to avoid the warranty. Now, some people use a very, very tiny dip, or or for like Aerotech motors, they coat the top of the motor with pyrogen. Um, you certainly want to avoid the older copperhead Aerotech igniters, the two little foils. They're very unreliable or in terms of clusters, at least for the average Rocketeer. And for the MGD um, type of igniter, you certainly want to slide the plastic collar back. And now we want to wire our starters in parallel. So a starter is basically a resistor that's going to heat up and light the pyrogen. So if over here on the right, if we have say two motor cluster, and we have a short, the other igniter can still light, and that can result in a thrust imbalance. Or if one igniter burns through, it can prevent the second one from uh, heating up enough to light the pyrogen. So that's why we want to wire our starters in parallel. And if you wire them parallel and one of these resistors actually shorts, it's probably going to prevent all the other ones from, the current's going to flow down that path and prevent the other ones from heating up at all. Um, and with parallel igniters, that's going to require more current. So you're going to have to calculate the current that you're going to need. And again, I recommend testing. And part of your checklist, you should always check the continuity, and you always want to use the same type of igniters in a cluster that have been, if you dip, that have been dipped the same way with the same dip. And it's a very good practice to match the resistance, because that can affect the rate that they come up to heat, and that can affect the time that the motors come up to full thrust. All right. So in terms of techniques for wiring starter leads, there's three different ways you can do it. On the left, we have a pigtail, uh, which can apply to a two motor case. You just wrap the leads together, although you're very limited in geometry. However, you can overcome that by soldering pigtail wires on each of the leads and then pigtailing them back to a center point. In the middle, you have a bus bar situation. Um, so you have two copper wires and you attach the leads to each copper wire. Uh, the one of the downsides of this is that it still doesn't really overcome the fragileness of SD's igniter. So you have to be careful, because all this attaching the bus bars can introduce additional movement and break them. I also recommend actually start soldering the igniters to the bus bar if you use a bus bar. And on the right, probably the most popular way for clustering motors is the whip clip. So here you have a pair of alligator clips for each motor that lead back to a pigtail situation. Now the disadvantage here is that you're introducing another connection, and that these alligator clips can touch together and short. So now, um, as I mentioned, the Estes igniters are very fragile, so that here's a tip for inserting them. I like to take a pair of needle nose pliers and protect the end by holding it tight. And then I like to bend the leads a little bit apart. And then you can use the needle nose pliers to slide the igniter in and insert the plug, hold it there while you insert the plug. And you certainly, I didn't put it on the text, but you certainly want to use the right size plug, because if you put one that's too big, it can actually stay in the motor and travel up with the provide kind of a leash and flip your rocket over. Okay, so when you insert high power starters, you want to make sure you get them inserted fully. And I like to, a good practice is to actually mark on them with a marker where the end of the rocket is. Again, you don't want to break the bridge wires, their stuff, or knock all the pyrogen off. And it's a good idea to put a little zigzag at the bottom and put the motor cap on, and that acts as a spring to hold it up against the top. If you don't get the igniter inserted all the way in a composite motor, it can actually just kind of burn and not come up the pressure, and it can melt your rocketry case, as well as not providing any thrust. So connecting starters. You want bare metal against bare metal, and this is certainly one of the most important slides of my whole presentation. You want to clean the alligator clips off, and you want to you want to strip the leads back and put multiple wraps around, and you can wrap it in such a direction that it's going to hold those jaws shut. And then not shown here is you can wrap the insulation around one time, and that acts as a little bumper against shorts. Okay, and lead retention and management. Um, Again, this is more complex for clusters than single motors. So a good trick for low power motors from which I learned about from George Gassaway, is you can actually use gum to secure the igniters, especially if you're using those MJGBP igniters. You have to be careful with masking tape, because you can actually, your leads can actually stay attached, and again pull the rocket sideways as it goes off the pads. You want to make sure that you have plenty of wires for leash, so that the leads can move up with the rocket and help late starting motors light. And to guard against shorts, you can put, certainly if you're using like a whip clip, you can put masking tape around one of them to act as a protective insulating bumper. Okay, and here we have a tractor rocket again with clusters. You can see I've soldered pigtails onto Estes igniters. That goes back to a whip clip, and I've done lead management by taping my leads to poles. Now, something I didn't do here is I didn't protect very well against shorts on the whip clip, although there's sufficient room here to space them out physically. All right, so let's just take another breather and enjoy some more pictures of cluster rockets. On the left, we have a nice tractor rocket, non-canted, by Bruce Strong. And on the right, we have another Bruce Strong rocket with canted motors. And on the bottom, we have a 5 motor cluster with straight motors in a circular pattern. All right, that takes us to launching, which will supply current. The starters will heat up, and the motors will come up to full thrust. All right, so for low power motors, I encourage the use of Estes Pro Launcher, which you can launch 3 motors at once. Has a built-in whip clip. Basically, you always want to use fresh batteries. So after kind of every you do 1 or 2 launches, you should put a fresh pair of batteries in there. In high power, lots of motors need lots of juice. So here we have a LiPo motor on the left, or a nice motorcycle battery. I don't have a lot of experience with LiPo motors and cycling them over and over again, how they hold up, because in cluster launching, you're basically providing a short. I do know that lead acid batteries can take a lot of abuse, and our club certainly has lead acid batteries that have been around for 5 or 8 years. You want to use large gauge wire because you have a current drop, and then you want to have nice sturdy connectors. Here's Anderson power pole connectors. All right, for launch controller for clusters, you want to have a nice, good launcher that can supply the current. Here's one that our club member guides Wadsworth built for me. And here, actually, you can in white here you can see a nice whip clip that he specially made for me for the Deuces Wild drag race. It has nice heavy duty wires and nice sturdy alligator clips with insulation on here. Now, one very important consideration for high power rocketry is that your cable run is going to provide a current drop, as well as the inductance of the conductors are going to oppose the turning on of the current. So you want to use a relay box if possible. Now, a relay box sits right beside the rocket, and the controller will supply a signal to the relay box, which in the high current battery is placed, activated by the relay. Um, and this mitigates the problem of long cable runs, and you can build one yourself, or a quick burst supplies a nice cluster box. So at our CMAS club launches, even on the low power pads for cluster, on the pads that we do clusters, we have relay boxes as well, just to increase that reliability that will supply enough current to get our igniters to heat up and launch. For launch considerations, you want to launch in low winds, have the launch angle away from the crowd, and you want to orient the rocket. So if there is potentially a thrust imbalance, that it's away from the flight line. So for example, the Deuces Wild, you can put the plane of the motors parallel to the flight line, and you get a better view that way anyway. So Kip in the overview talk talked about go fever. So you have your heart set on, you go to launch, you want to launch 5 rockets, and you haven't launched that cluster, and it's getting to the end of the day and it's kind of hot. Well, maybe you want to just save that cluster for another day. Certainly, my greatest mistakes in rocketry have been become because of go fever, and over a beer sometime, maybe I'll tell you about those. And you also want to note the NAR safety requirements for complex rockets. You need stronger, more standoff distances, and you can look that up. I'm not going to go into it in detail today. And another consideration for clusters is recovery, because cluster rockets can be heavy, and even if you drill those delays down, it still may be too long. So you might want to need to use electronic deployment, especially when you take into consideration if not all your motors go off, your rocket's even going to go to a lower altitude, and even the minimum delay may still be way too long. Okay, so that's lots of things that can go wrong. So what can go right? And we're hopefully this talk will help you become get you excited about clustering and more proficient. So on the left we have a 4-inch Deuces Wild in this Boris Gatan spinning saucers, and over on the right we there's a monocopter that I 3D printed with 3 motors. All right, now let's very briefly, because I'm running out of time, let's talk about the advanced topics. So one thing, and this could actually be a whole second talk, maybe next year at NARCon, but I'm briefly going to touch upon these topics. So the first thing is mixing black powder and composite motors. Now, remember, I talked about the composite motor and all those things that have to happen, uh, and that takes time. So there's basically black powder motors. If you apply current at the same time as the composite motors, the black powder motors will go off first. And that's a very important thing that you need to take into consideration if you're mixing black powder and composite numbers. And we can see that in this little video, and I'm supposed to turn off this sound. And this is in slow motion. I'm applying current simultaneously to an A8 motor and a composite motor. And let's see what happens. Um, uh, Maybe. Come on. Well, the AV gods are not very friendly to me today. But over here on the right, you can see on the top panel, you can see the black powder motor firing, and then half a second later, the as you see in the bottom right panel, the composite motor is coming up the thrust. Now, I didn't plan this way, uh, but the black powder motor is completely finished burning. It has a thrust time of 1/2 a second, and the composite motor hasn't even come up to pressure or full thrust at that point. So, one way people deal with this is to have a delay relay, two sets of lines going to the black powder motor and a different set of lines going to the cluster, and they have a tunable delay. Of course, you need to figure out what that delay is. So, that's a very kind of advanced topic. Um, now, I mentioned another. So rather than individual igniters, a technique that people do to launch large number of motors is to use a flash pan. So this is a metal or cardboard pan filled with a thin layer of black powder, and that's placed. Well, you need to have your motors and or sets of motors in a plane. Light the Your igniter lights off the black powder, and then the black powder lights off all the motors. And it's a very effective way to light large numbers of motors, but it can also burn the bottom of your rocket. Now, somebody has developed something called a spider. So this is a chamber of black powder, and there's a tube that goes up to each motor. Now, this is very, very effective at lighting cluster motor, but the trade-off, of course, you're limited to the specific geometry of these tubes, and it's not very flexible. Okay, and another useful thing for high power motors is a cluster box, which is a high power current source specifically designed for clustering. And Boris Katan talks about one of these in a sport rocketry article, and he probably has the record for the number of simultaneous cluster motors lit with individual starters. Of course, with the flash plate, you can launch much more, but probably record for individual starters in a cluster, probably in the 35 to 50 motor range. Okay, and then also um, there's a note about thermite starters. Okay, so in summary, uh, clustering is very cool, and I encourage you to crawl, walk, run. You want to start with low power before high power. You want to start with 2 or 3 motors before you go to 5 or 6 or more. And I'd recommend starting out with kits before scratch, and certainly you want to do low power clusters before high power clusters. And um, you want to these techniques lead into staging and air starts. And on the left, we have a Deuces Wild. I like to joke that even an Estes Alpha looks like a high power rocket if you zoom in enough. And on the right, we have a cluster launched at Deuces Wild at MDRA by Bob Cohen and Bob Utney on 2 O motors. And they launched, so I guess the converse is true. If you zoom out from a 500-pound rocket, it looks like a regular Deuces Wild. Um, so they launched this in 2022 successfully, in 2020 or so 2021 and 2022. The nozzle failed, and it bent the launch rod way over, and it launched at such a great angle of attack it didn't recover a vertical flight, and it flew off in a ballistic trajectory. Again, they had the plane of the motors parallel to the flight line, and it went off to the side. All right. So as an exercise to the reader, develop your own risk analysis, and clustering looks cool, can be fun and rewarding. There's, of course, additional safety considerations, crawl, walk, run, work through your own risk analysis, and learn from your mistakes. Certainly, not all my motors went off when I was going off. Keep a logbook of what happens. And I like Kip's advice also: slow down. Don't work through things carefully, master the skills, and mastering clustering is a good way to lead into air starts and staging. Okay, and thank you. And I have a lot of references in the back. And here's a shameless plug for the sport rocketry articles I've written. And there's more stuff in the Deuces Wild in the back. And I apologize about the AV problems. And we probably have one or two time for some questions. Okay. Uh, Q-jet motors. Yeah, you need these little fine igniters. They're very fragile. Um, um, they're easy to break. Or upscale Deuces. Yes, Flisklitz is marketing a 3-inch upscale Deuces Wild. That's actually based on one of my prototypes. Slides are not advancing. I apologize again. Um, oops. Y- Unfortunately, in presentation mode, I couldn't see the chat or the uh, QA over here. So I think I'll certainly be around during the rest of this conference. Um, and can have side discussions, or I'll be certainly happen to answer the slides. So there's a ton of material here, and the slides are available for download as well. So thank you very much for joining me today. And again, I'm sorry about the AV karma, and take care. Right.